So chapter 8 is all about exponential growth and decay, and really about logarithms as well. We'll get to that stuff later. First we're going to talk about exponential growth and exponential decay. All of these come from the formula y equals a times b to the x, and the sooner you can get in your head what a, b, and x stands for, the easier these are going to be, just different variations of them. For exponential growth, a, so this value right here, that is not attached to the exponent. All exponential growth and decay problems have an exponent here. A is your initial value slash your original amount. Okay, and it's the same for both. Okay, this value is also the y-intercept on a graph. Okay, it also represents it, and here's why. Anything on this y-axis has a value of 0 in the x spot. So if I plug 0 in here, anything to 0 power is 1. This whole thing will be 1 times a. Well, it's just a. So matter of fact, I'm going to go graph that right away here too. 0a. I know it looks like 0, 1, but this graph could be going up by 2s, by 5s, by whatever it wants. 0a on both of these. Okay. Now, the next part is in exponential growth, b is called the growth factor. It is what we are multiplying by, not factory, excuse me. Growth factor. And in the growth factor, that means that that b is greater than 1. Makes sense. If b was 1, 1 to any power is 1, times a is just itself. It would just continue to be itself. It has to be greater than that to make growth. For the decay factor, it has to be between 0 and 1. So this is 0 less than b less than 1. What that means is it's going to be a decimal or fraction between 0 and 1. Okay. Alright, so then you've got x. X is the number of time periods. It's not just years. It's sometimes you might, and it's the same for both of these, by the way. Sometimes you might have to divide. Or multiply the number of years per number of times per year. We'll see what that means a little bit later. Okay, just write that down. Again, maybe go back and hear me say it one more time. X is the number of time periods, and the number of time periods, if it says yearly, is just years. If it says monthly, it's just months. But if it says every 6 years over 24 years, then it happens only once every 6 years. So after 6, 12, 18, 24. So you have to kind of manipulate what the data is asking you to find. If it happens quarterly, we'll get to that later, then that's 4 times per year, and that affects some things. Monthly is 12 times per year, etc. For now, this section is going to be pretty simple. All exponential growth graphs are going to have a y-intercept there, and they are going to increase what's called exponentially from left to right. Okay, growth decay, or excuse me, exponential decay is going to kind of start up here and go down to there. Now notice one thing I want to make sure you don't do is go past the x-intercept, because these graphs don't. They shift sometimes when we do some random things to it, which we're not going to do. We're going to talk about that a little bit tomorrow in terms of what that looks like, but we're not going to really put the work into it. Basically what you need to know is nothing goes below the x-axis. How we say that, by the way, is all of our values are above the x-axis, so all the y values are going to be positive. So my range, which is my y values, is greater than 0, and it is the same thing for both of these graphs. What I'm trying to tell you there is, again, these graphs stay above the x-axis. Okay, and then you've got a domain, and domain is your x values. Well, the arrows tell you it keeps going to the left, it keeps going to the right, so we call this all real numbers. And you say all, and then I just put a couple of L's and an R through it. Okay, all real numbers. That's good enough. Okay. Alright, so there's some key words that as you're working through these problems you're going to have to recognize. If you see the words increase, doubles, which of course just means times 2, triples, which of course just means times 3, growing, and growth, Those are keywords within these story problem type problems that when you see that, that should trigger this is a growth problem, not a decay problem. Okay, decay problems should have the words decrease, depreciates, especially when you're talking about the value of an item, specifically cars, depreciate from the minute they leave the lot. Leaves, like how maybe cold medicines leave the bloodstream after every hour or so, and then shrinking. Okay. Now down at the bottom here, we're just don't make this harder than what it is. All it is talking about is it growth or decay? And what I want you to recognize is growth or decay are specifically found from B. Okay, and if B is greater than 1, then it's growth. If B is less than 1, it's decay, and it's as simple as that. Okay, so once you know your growth or decay factor, I would say do this first. Okay. Then I can just write growth or decay, and I'm trying to find the initial value is A. So I'm just going to go through the initial value. There's 2. The growth decay factor is 3. Well, 3 is greater than 1, so it is growth. I'm not asking you to write here what I have in parentheses. I'm just trying to have you see that it depends on this line. For instance, if I go to the next one, my initial value is 2. My growth decay factor is 0.3. Well, 0.3 is less than 1. It's never going to be negative. I tried to say that up above. That's why it's not going, it's between 0 and 1. Okay. This is less than 0, so that means it's decay. Take a second and pause it. Try and do 2, 3, 5, and 6. They're super easy. You see what you're looking at. Try it now. So again, I'm just looking at this row. When it's greater, it's growth. Simple as that. Less than is decay. In class, I purposely messed this up. This is growth. In class, I put decay here, and people said, why is that decay? And I said, because of the 0.32, and then people believed me, and I was just messing with them. This is always based on this number. Again, that's less, so less decay. Okay, that's the easy part, the first part here. Let's get to the next page. Thought this a little different this year. I'm going to start actually on example 3 and 4 here. So we're still going to use that same formula though. We're still going to use y equals a times b to the x. What I think is easy to do is recognize these first, then just plug it right into this equation. So I'm going to have y equals, let's identify a, b, and x. A, again, is the initial amount. Well, it says initial population is 2. So a equals 2. Okay? B, that is your growth or decay factor. This is tripling. Tripling should trigger right away. It's growth. And what does triple mean? Triple means times by 3. Well, then I'm multiplying by 3. That's what I'm doing. Okay, my x is my time periods. Now it says after 24 years, right? That's a big deal. But it also says it triples every 6 years. Okay, so what I've got to take here is, how often does that happen? After 6 years, 12 years, 18 years, 24 years. That's 4 times, right? Of course it is, because you take the number of years divided by every 6 years, and it occurs 4 times. 4 time periods, I guess, is what I like to use for my verbiage here. So let's plug them all in now. 2 times 3 to the 4th. Simple as that. Plug it right into your calculator. Why? Or you just turn it on. Press 2 times 3 to the 4th power. The caret key above the divide sign is what you use to go to the power of. Plug it right in, you should get 162, but of course it is, because 3 to the 4th power is 3, 9, 27, 81, and 2 times 81 is 162. You don't have to show me this work, but it should always work that you do the exponent before you multiply. Always, 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 always got to do PEMDAS says it too, that first. Pause it once, try number 4. It's going to look a lot like number 3. Try it on your own. Go back. Alright, so I think I've got all my information here. 1500 is my initial amount. It triples every 4 years over a 20-year period means it's going to happen 5 times. Again, I could multiply this out if I want, but you do not need to show me that step. You can plug it in as 1500 times 3 to the 5th power. Okay? I get here, but I get kind of a big number, which is not really that feasible, but possible, I suppose. People. Make sure you're labeling people. I did that intentionally. We didn't label here. Hopefully you're thinking, Mr. Searsmo, you need to label that, and you would be correct. Rabbits. Okay. Let's go back up to the top here. Now there's percent increase and there's percent decrease. Okay. Think of what is a whole in math. I just about said it there. It's 100%. Okay. So if I take 100% or something and it increases in percent, I would add that percent. If it decreases in percent, I would subtract that percent. What I mean is, when I have a percent increase problem, and you'll see it where it'll say increase 4%, 16% leaves should trigger decay. Okay, and we'll talk about it with decrease here too. But for both of them, we start with 100%, right? A whole of something. If it increases in percent, I want to add whatever it tells me. Okay, so plus increase. That will give you 100 and blank, and then you would move the decimal over 2 places. Left. I'll give you an example of this in just a minute, but if it's percent decrease, we take 100 minus the decrease. Equals 1, I'll just put an X here, equals, I guess I don't want to really say it because it'll be less than, and then you do the same thing, move the decimal over 2 places to the left. Kind of what I'm saying here is if I have a 5% increase, what I would do is I'd go 100 plus 5 to get 105, and I'd move the decimal over 2 places to get 1.05. Remember, when it is no decimal there, it's always at the end. Okay, if I had a 5% decrease, I would take 100 minus 5%, get 95, move it over 2 places, and get 0.95. That's kind of how this works. Okay, so let's take a look at this first one. Again, let's identify A. We know it's going to be y equals a times b to the x. Let's identify a being x. A, it starts here, $668. My b. Well, B, it doesn't say triples, it doesn't say doubles, it says it increases by a percent. It says 4% specifically, but if you increase by a percent, then you just add 100 plus the percent of increase, which is 4%, and I get that, and move the decimal over 2 places, and that's how I get B, 1.04. Okay? So, let's start plugging this stuff in here. We got 668 times 1.04 to the what power? X is, let's see, 4% per year from 95 to 2010, which is 15 years. So it's 15 divided by 1, but it's just 15 years here. 15 goes up there. Again, plug it in just like you see it. 668 times 1.04 to the 15th power. Get your answer, which would be 1203.03. Okay. Number 2, I kind of started having people look at, and then I realized because it's a decrease problem, we should probably talk about this. But your A is still 15 milligrams here. Tells me right there. Your B is 100, and again it says leaves. So I got to go minus the 16 to get 84. Move the decimal over 2 places to get 0.84. Alright, let's start plugging it in. 15 times 0.84 to the, well, how many, let's see, 8 hours. But it goes every 30 minutes, right? So it would be 2 times per hour times 8 hours, right? So that's going to give me 16 time periods. So again, sometimes you got to divide, sometimes you got to multiply. It just depends on what the problem is saying. So I just take that to the 16th power, and I plug it in. 15 times 0.84 to the 16th power, and you'll get 0.9216. If you just say 0.92, that's good enough, but you better make sure you label it milligrams. That's how it works. Okay. Down on the last one, If you remember how we checked the sine functions when we had a line and we had like a curve like that and we had to find that point of intersection, that's the kind of thing this question is asking you to do. Again, this is an ACT, SAT type of question. It's something that we got to get used to. Now what it's saying here is that there's a population of about 100 million and it's growing at 1.53%. So really I've got 100 plus 1.53, which is 101.53, and I moved the decimal over 2 places to get 0.10153. And then of course they added the 1 to that. Remember, excuse me, it's not point, it's 1.0153. That's how they get this number here. Okay, sorry, it is right here. That's where they get this whole function, actually, is with 100 times. Then it says, in years after 2000, use this model to predict when it will reach 109 million. The population is right here, so really we're just going to replace that. 109 equals 100, 1.0153 to the x. Now there's something I could do right here with logarithms that we'll find out later in this chapter, but not right now. Right now we can just literally go to our graphs, push the calculator on, go to y equals, y1 is going to be on this side, y2 is going to be this entire side. Now remember, when you put this to the x power, you use your caret key, and the x is the button right next to the alpha green button. Okay. Now you've got that there, plug it in, you're going to get a graph, you're going to look and see where does it kind of cross, but if you can't even see it on your graph because your x and y values are not good enough, are not wide enough, you can fix your window, expand it to maybe negative 500 to 500, something like that, just something big, or just maybe negative 10 to 10 for your x values at least. Don't even need you to do that. You can press intersect, so go second trace, 5 for intersect, enter, enter, enter. You're looking for one point of intersection here. And the point of intersection is like 5.67. Okay, what that means is it went through the first 5 years, so by 2005, and then in year 2006, it started happening. Okay, so it got to 109 million. So my answer here is A. It did not happen before 2000. By 2005, it happened in 2006. Okay. All right. So, anyways, that's the least of your concerns. Hopefully, you understood what was up here. This is really what the crux of this section is all about. Your homework is the next couple of pages. I would give you one hint on one of these. They're not very difficult. They're really not. You should be able to fly through this. Actually, is that right here? A lot of people struggled with number 3. Basically, think of it as, remember, it's a times b to the x, and we can see the number that's attached to the x. What number could I put here that won't change the value? Some people will make it 0, but 0 would make it go away, right? It'd be 0 times everything is 0. So 1 times 1.5 to the x power. That should help you fill in the table if you're not getting that. Have a good day. Sorry for the lateness on this. See you tomorrow.